we are about 20 minutes late, but we'll cut it from the lunch break. It's a real pleasure to have the next speaker, Michal Irani, who actually was a student in Jerusalem and did a PhD with Shmuel, and all one big family in it. So she's doing the Weizmann Institute now. She's doing absolutely amazing work in vision. I hope she'll be able to surprise us.
Am I supposed to put anything on?
Yes, please put this on. They hear it without it, but this is much easier.
Okay, can you hear me? Yeah. All right.
Again, I just want to tell everyone, those who don't know, we record all the talks and everything is going to be available on the web eventually. It's not just us being about it.
All right, so actually, first of all, I want to tell Tali, who keeps saying that we disagree on, that I disagree with him on things, that I actually have, I agree with you on lots of things. I was very inspired actually by the talk.
Not everything we disagree.
Not everything, but we don't agree on everything, but you'd be surprised how much we agree on. I totally agree with you. The prediction of prediction of information is very important, and I totally agree with you that the world is non-parametric and so on. All I was saying yesterday when we were having this debate is that it's not necessarily sequential in time. That's what we disagree on.
I'm going to take all the fun away.
No, I totally agree with you. There's nothing I disagree with you on. So anyway, this is a very broad audience, and many people here are non-vision people. So I decided to give a broad talk covering several things we did over the past few years, and therefore this is going to be more of an in-breadth talk rather than an in-depth one. I'm not going to be able to go deeply into the technical details, but I will try to give at least the intuition behind theoretical ideas, and people, of course, are welcome to ask more questions during or after the talk. And some of you have heard this talk, so I apologize ahead of time. I hope it won't be too boring for those who have. Anyways, so what is it that we want from a good artificial seeing system or from a good visual browser? We'd like to be able to give it an image of an object of interest, and for it to be able to find other instances of the same object despite the large variability in its appearance, a heart in this case. We'd like to be able to give it a dynamic behavior of interest, some short video or something we're interested in, and for it to be able to detect other instances of the same type of behavior, again, despite the fact that people are wearing different clothes and the backgrounds are completely different and so on. Now, the way this has typically been handled by the vision community over the past decade or so has been, let's train on lots of examples. Let's train on lots of hearts, lots of walks, lots of horses, lots of flowers, lots of so on. And from these, extract informative parameters or features or models. And then when a new action or object comes along, we'll use these models or parameters or features. And from these, we will classify it accordingly. And there has been tremendous progress in the vision community over the last decade using these kind of approaches, and Arnold has showed one such example yesterday. And the problem, however, with these kind of approaches is that it's restricted to a small set of predefined classes of objects and actions for which we can provide enough examples with good enough localization, with large enough variability of appearance, and so on. And it's not realistic to assume that every single object out there, and definitely not every single dynamic out there, can be modeled and can be parametrically modeled, and that we can provide enough examples for each and every one of them. And the question is, can we still do something reasonable when we encounter something new that we have never seen before, even if we haven't been given lots of examples? So we'd like something which is more data-driven, something which is less parametric. What I'm going to show today is how, one such approach is how by exploiting the internal redundancy of data, we can obtain such results. And I'll explain what I mean by that. There is so much spatial redundancy in images, and there is so much temporal redundancy in a video sequence, that if we're able to detect this redundancy and exploit it, this often provides us all the statistical information we need in order to perform very complex visual inference tasks without any prior examples, with very little training and often no training whatsoever. And we call it inference by composition. We do visual inference by composing little chunks of the datum. And this gives rise to a wide range of visual inference tasks, including complex object and action detection of the kind that I have just shown without any prior examples, predicting visual information, talking about likelihoods of never before seen visual data, detecting the irregular and unexpected when we don't know ahead of time what they would look like, generating visual summaries, segmentation, super resolution even from a single image, and various other applications. I won't be able to talk about all of these, but I have selected a subset of these that I will talk about today. Okay, so let's start with the first example, the problem of detecting similar objects and actions. Now, if I show you these 4 images, I think you would all agree with me that these are different instances of the same object. It's very hard. But what's common to those images? If you look carefully, you'll note that they don't share the same colors, they don't share the same textures, they don't even share the same edges. Here there are triangular edges, here completely different edges. Yet it's obvious that these are images of the same object. So what is it that's common to them? Or if I show you those images, 2 peace signs, one of people standing on a hillside, skulls on the grass, don't share the same colors, texture, edges, yet it's obviously the same object. So what is it that's common to them? What we say is common to them is the fact that despite the fact that these 2 patches are very different from each other, they share the same geometric layout of self-similarities within the image. And this is what's common to those images. So it's those internal self-similarities that's common to those images. So we're going to start matching images by using those internal self-similarities. So we devised a descriptor, which we call the self-similarity descriptor, which can be computed in each and every pixel, and it's computed the following way. For each pixel in the image, we take a small patch around it, say 5 by 5, and correlate it with a surrounding region around it, say 40 by 40. And when we correlate this patch against this region, we get this correlation surface. Bright regions are regions where this middle patch is similar to, dark regions are regions where this patch is different from, and so on. Now, in principle, we could have computed such a correlation surface for each and every pixel of the image and started comparing correlation surfaces across images. But there are 2 problems with this. First of all, this is too much information to keep. If this is 40 by 40, this is 1,600 values per each pixel, just too much data. The second problem is it's too accurate. We want to be able to say that these are 2 similar objects, even if they're slightly non-rigidly deformed relative to each other. So what we do, in order to solve both of these problems, is we quantize this correlation surface using a log-polar quantization, with bins growing larger as we get farther away from the central pixels. Okay, so we take, let's say, 4 different radii, 20 different angles, or something like this, and in each bin we take the maximum value. And this gives us our self-similarity descriptor. Okay, now this descriptor is both compact; it has only 80 values. Okay, but it's also non-rigid to small affine deformations. If I slightly scale or rotate this correlation surface, the self-similarity descriptor will remain the same. And also it's insensitive to small non-rigid deformations. It doesn't care exactly where the maximum falls within this bin. Okay, so let's see what we can start doing with these kind of things. So for example, if we take those 2 images, and let's look at those 3 patches, and here are the 3 other patches, the corresponding patches, you'll see that those patches are very different from each other. But if you look at the self-similarity descriptors, these are very similar to each other. For example, patch number 1 here and patch number 1 here are very different from each other, but their self-similarity descriptors are very similar. Okay, so we can start finding correspondences across images using these kind of self-similarity descriptors. Or, for example, if we take this template image and say, find something similar to that template image in this image. Okay, we would like, ideally, to find these 2 flowers, okay, even though they're slightly different. So what we do is we densely compute the self-similarity descriptors in this template image. This gives us an ensemble of self-similarity descriptors. We also densely compute the descriptors in this other image. And now we search for a similar ensemble of self-similarity descriptors, similar both in their geometric location and in their relative geometric location and in their values. And this gives us a likelihood map of where this thing is likely to be, where we found high similarities to this ensemble of descriptors. And you see that there are 2 very high peaks in the correlation surface, but if we look at what they are, they're exactly these 2 flowers. Okay? And we can run this template against other images. They can be real images, they can be synthetic images, and in all these cases you get the peaks where you would expect it to be.
I probably missed it, but is also rotation invariant? I mean, in the B sign, the the patch 1 and 1 were very similar, but you have, I mean, the object on the same rotation. If you rotate it, let's say 90 degrees, it's still...
You're not talking about the descriptor, you're talking about the patch.
Right.
No, it's not. The way it depends what your similarity is, okay? When you run this correlation surface, depends on what you do. If you just do sum of square differences between the patches, it will be very sensitive to rotation. If you could take a distribution of descriptors inside the patch, then it might not be. It's very dependent on what your similarity measure is, okay? Right now it's not. We just sum of square differences between the patches. But the self-similarity descriptor itself can breathe. It's also not invariant to scalar rotation, but it's insensitive to plus minus 20% of scaling and plus minus 10 degrees of rotation or something like that, okay? But you can, by the way, extend this to be scalar rotation invariant. Okay. So let's look at a more complex template. Here, for example, is this template image. We run it against those images, and here are the peaks that we get. Okay? And it's not true only for this particular template. We ran it with other kinds of hard templates. In all these cases, we got the peak in the correct place. And remember, there's no training here. We don't learn first parts and then look for this. It's just based on a single example. Or here's an example of a face. We run it against these faces. And we just take this template image, right? We don't know it's a face. And this is where the peaks of the correlations are. Or we can just sketch a face and run it against this image, and this is what we get. Okay, and we took this idea of sketching even further. We sketched this person standing like this. Okay, ran it against those images, and here are the peaks that we get. And again, remember, there's no edge detection here. Okay, there's no. It's just using the raw color information from the images themselves. Okay, and these are the peaks defined as arrangements of self-similarity, same arrangements of self-similarity descriptors. Now, what happens in video? Well, the notion of self-similarity in video is even stronger. It's even stronger over time than it is in space, because people don't change clothes from frame to frame, the backgrounds don't change from frame to frame. If I have two people performing the same kind of operations, but wearing completely different clothes, each one of them will generate, over time, the same geometric layout of self-similarity descriptors, even though their clothes may be very different from each other. Okay? So in video, the whole thing is done in space-time, okay? When I say space-time, I mean here is an image. You stack all the images one after the other, so this is x, y, and time. This is the space-time volume generated by the video. For each pixel in the video, we can compute a space-time self-similarity descriptor in the following way. We take a small patch around it, say 5 by 5 by 5, correlate it with a surrounding space-time region. This gives us a correlation volume, which we can again quantize in a log polar way spatially and in a logarithmic way temporally. Okay, quantizing it logarithmically in time allows us to be insensitive to different speeds and behavior of people, or not speeds, in behaviors, okay, in temporal behaviors. And we can compute this self-similarity descriptor for each and every pixel in the video. Okay, and now we can start doing things like action detection using these kind of things. For example, if I take this ballet turn with the two hands up, I can compute the space-time self-similarity descriptor in each pixel in this short video clip. We've downloaded this clip of Royal Ballet of London. Again, we compute the self-similarity, the space-time self-similarity descriptors here. And now we look for similar space-time ensemble of space-time self-similarity descriptors, and whenever we find something similar, it will be high. Jumping jack, okay, and run it against this video. Move at the top is the input, at the bottom is the output. Get rid of the cursor. Okay, but the notion of visual similarity can become much more complex. If I show you this image and ask you to find something similar to that, and you come across those two images, I think you would all agree with me that this image is more similar to that than this image is. But why? What makes it more similar? If you look very carefully, you'll see that none of those poses are found up here. Nobody up there is jumping with the two legs apart. Nobody up there is standing with the two arms above, and so on. So what is it that's the same? It's definitely not bags of features, okay? Or bags of words we talked about yesterday. In both of these cases, the foregrounds are bright, the backgrounds are dark. But there's obviously something similar to these things. Now, of course, you can say, and rightfully so, that we're intelligent people and we see lots of ballet images in our lives, and we know that this is ballet and this is ballet, and therefore we say it's the same. And this is, of course, true. However, there's something inherently similar to those two images. What makes this image more similar to this image is the fact that it's very easy to compose this image like a puzzle, like a very simple puzzle, from this top image. For example, this part over here we find here, and this part over here we find there, and this part we can find there, and this part approximately. It's very important. Okay, something similar, not exact, and this one we can find there, and so on. Or in other words, the description length of this image, given that image, is a short one. Okay, if we want to code this image, given that we've already seen that image, we don't need lots of bits. We get lots of savings in bits when we code this image, given that we've already seen that one. Now, it's not that we will not be able to build this image like a puzzle from this one. We will. But this time we're going to get lots of tiny little pieces. Okay? Or in other words, so if this was a simple puzzle of a 3-year-old, this is a puzzle of an adult with lots of tiny pieces. Or in other words, the description length of this image, given that image, is a long one. Okay? We need lots of bits in order to code this image, even if we've already seen this image. Okay? So we call this similarity by composition, and this is work together with Owen Boyman that we did in NIPS 2006, and it proposes a theory for matching two different signals, okay, both globally, finding similarity between two different signals, even if they're of different size, okay, according to how easy it is to build one from the other. These could be two different signals. It could be two different parts of the same signal. Okay, it applies to many types of signals. We've used it for images, audio, and video. Okay, and it applies to various inference tasks. Now, I can't go into in depth into this thing, but I want to just give one slide explaining a little bit how the gist behind this theory, if I may. So, what's the general idea? The idea is the following. Remember, we want to ask how likely is this image given that one, okay? Or how predictable is this image given that one, okay? So, in general, we would like to ask a question like this, but let's ask a simpler question. How likely is this region given that image, okay? Now, that's a simpler question because we can ask, for example, how likely is this region to be in this particular position in this other image? That's something we can compute. We can compare them up to some non-rigidities, allowing for some similarities, and we don't expect it to be exactly there. Okay, but we can ask how similar is it from that and extract the likelihood measure from that. Okay, so that would be the likelihood of the region R in at certain position T in the reference image. Okay, but that's only in one position. In order to get the likelihood of R given ref, we have to marginalize over all possible positions in the reference image. Okay, and that gives us the likelihood of the region R given the reference. So this is how we compute the likelihood of a region in one image given another image. But that's not enough. Because, remember, we want to grow regions that are as large as possible. We want to make our puzzles with largest possible pieces. And the larger the piece, the smaller its likelihood. Okay? Because if you think about it, the most likely pieces will be tiny little pieces of uniform regions. They will match in the best possible way, and they will be found abundantly in the image. But that's not what we're interested in. So it's not really this term that we're interested in. What we're interested is in this likelihood ratio. The ratio between how likely it is to generate R, the region R from the reference, versus how likely it is to generate the region R from a random process. Okay? How likely it is to generate it at random. Okay? For example, small tiny pieces, tiny uniform pieces are very likely to generate at random. On the other hand, large textured regions are very unlikely to be generated at random. Okay? And it is this likelihood ratio that we try to maximize when we grow those regions. Now we know that the number of bits required in order for coding a random variable is minus log of the probability of the variable. So if we take the log of this thing, this is exactly going to give us the savings in bits between the number of bits required in order to code R given the reference image versus the number of bits required to code R given a random process. And it is this savings in bits that we want to maximize when we grow those regions. Now this is, of course, only one particular region. Nobody gave us that region ahead of time. Okay, we're trying to ask what's the likelihood of how much savings in bits we get for the entire query given the reference. So in principle, we would have to marginalize over all possible segmentations of the image, and this is, of course, computationally intractable. But in practice, we show that this term can be bounded both below and above by terms that are easy to compute computationally, and these are the terms that we compute. Okay? So I know that this was very quick and brief, but this is the basic idea behind our theory of similarity by composition. So as I said, it's good for comparing between two different signals. We've used it both for image classification, for action classification, and also for speaker recognition. Okay.
How different is it from the old idea of, actually, which is due to Kolmogorov, and then used, mentioned by Yaakov Ziv, for example, in the of compressing together and separately?
Yeah. So I just had a conversation about this earlier this morning. I actually think it's very related. Okay, if we think about Ziv and Lempel, if we think about the Ziv Lempel kind of coding, it's a 1D process and it's exact. Okay, this is in a way is a 2D process and it doesn't have to be exact, but I think it's very tightly related.
So it's a universal type of measure.
I totally
boils down asymptotically to mutual information.
I agree. All right. So, so we can use this in order to say how similar is one signal to the other according to how it is built. But we can also start talking about likelihoods of visual information given that we've never seen before, given other visual information that we've previously seen. And this allows us to do various interesting things. For example, it allows us to predict visual data. Now, what do I mean by predicting visual data? For example, if I show you this sequence and ask you what's behind this girl who's waving her arms, you'll have no problem telling me what's behind her. Yeah. And by the way, what I'm going to show now is joint work with Defects. So you'll have no problem telling what's happening behind, right? You'll tell me, sure, there's grass behind there. And at some point, we wait a few seconds, this girl is going to jump behind her. Here, right now, this girl is jumping behind her. How do you know? You have never seen what's behind her, right? There could be lots of things behind her. There could be a zillion and one things behind her. There could be flowers behind her. She could be patting her on the back right now. There could be lots of things. Yet we'll all give the same answer. There's grass and she's jumping behind. How can we all give the same answer if there's so many different interpretations of possible interpretations of what's happening behind? It's very simple. Occam's razor. We all give the same interpretation because this is the simplest, most likely interpretation of what's happening behind, given what we see in the remaining parts of the video. So this is exactly what we wanted to do. We wanted to throw this thing away and say, complete the most likely visual information given what we see in the remaining parts of the video. And this can be posed as a global optimization problem. Okay. So this is, for example, is the space-time volume generated by this video sequence. This is all the visual information you have in this video data. And again, this is X, Y, and time. And this is the whole generated in the space-time volume. And our goal is to complete the most likely information here, given what's in the remaining parts of the video. Now, this is very similar to the puzzle problem I talked about before, only now our pieces of puzzle are going to be space-time pieces, and we'd like them to fit very well with each other, both in space and in time, both with each other as well as with the surrounding information around the whole. Okay. Now, as I said, this can be posed as a global optimization problem, which is a simpler manifestation of what I talked about before, and actually it predated the theory that I talked about before. Okay, in a way it led to this. Okay, so our goal is to find this whole age, which is most likely given what we see in the other parts of the data. So we can we won't do the full-fledged with irregular shaped pieces. We do that, by the way, in other cases, but here for the synthesis we'll do something simpler. For each pixel in the video, we will ask, we expect, we would say this, if you were to give me, let's say you were to give me an age, and ask me to, I'll tell you how good, I'll give you a score of how good this age is, okay? I want this score because I want to be able to optimize it later. So if you give me a pixel, you give me an age, now for each pixel in the age, I'll ask, this surrounding space-time patch, is it found elsewhere in the video? Look for the most similar space-time patch in the video, and ask how similar they are. If there's no error between them, that's great. If there's difference, then that starts accumulating as an error. Okay, so we can start measuring for each patch the most similar patch in the video and maximize this similarity. I want for each and every pixel for its patch to be somewhere else in the video. That guarantees that I don't invent new information. And what I do is likely. Okay. Now, what we really want to find is the whole age, which maximizes this term. Okay, and this can be posed in an EM-like algorithm, which I will not go into the details now because of the short time. I will say, however, that in order to avoid getting stuck in local minimum, in Minima, what we do is we fill this whole thing coarse-defined, both in space and in time. This guarantees that both it speeds up as well as guarantees that we don't get stuck in local minima. So what we do is we take the video blur and subsample it both in space and in time. This generates shorter and shorter videos with smaller and smaller frames, okay? Until we get this itsy-bitsy tiny video, okay, with a very, very tiny hole. We do a very crude completion here, okay? And now we start propagating the results up both in space and in time, and each time we refine them using the EM algorithm. The crude completion guarantees a global coherence, and then the refinements, the local refinements guarantee local coherence. And all in all, we get something which is both globally and locally consistent with the surrounding information. So this is, of course, a greedy algorithm, but it produces reasonable results. So at the top is the input, at the bottom is the output. And we checked. The girl is not copied from any individual any other individual place in the video. In fact, her ponytail comes from one part, and her hand from another, and the leg from a third, and so on. And this is the most likely configuration the algorithm is able to generate, given the space-time configurations it has elsewhere in the video. Or if I show you this video and ask you what's behind the umbrella, you can probably all make an intelligent guess. And indeed, this is what the algorithm generates. It automatically completes the heads of people and the waves in the water and so on. And remember, there's no segmentation here. There's no motion analysis here. This is directly straight from the raw space-time color information. This is just the most likely space-time configuration of colors that it's able to generate given other space-time configurations of colors it held elsewhere in the video. And of course, it applies not only to video data, it's also to images. These are just 2D signals. If we remove this boy and ask for a completion of the most likely visual information, this is the most likely visual information it generates. Again, not perfect, but it's a greedy algorithm, but it does a pretty good job. And of course, we can use it in order to predict new visual information. I mean, hypothesize or say what's the likelihood of new visual information we haven't seen before. This is an extension of this work with Benissima Conveni, Owen Caspi, and Eli Shefman, where we take an image and we say, can we, I mean, we've seen the man behind the cow. Is it likely to have the man in front of the cow? I mean, not in terms of semantics, but in terms of visual interpretation. What the algorithm does is it generates the most likely visual interpretation given that image and this new constraint. Okay? And this is the most likely visual information it's able to generate under these conditions. And it's also able to give us a number of how likely this is. Okay? Or here is another image. Here is the man in front of the cow, or behind the cow, or above the cow. In all these cases, it would try to synthesize the most likely visual information given that image and those constraints, and will tell us how likely it is. Okay? Now, of course, this is also using for generating visual summaries. We talked yesterday about memory. If I show you this image, and I'd like to generate a small visual summary of that size, let's say somebody tells me, now, I have a restricted size. Of course, I can scale this down, but I will lose the resolution and will lose the aspect ratio of things. Or I can just crop a small region, but that will definitely not be very informative. I want to get the best visual summary I can, the best memory I have. Now, look at this image. If I, let's see if I hide it again for a moment. What do you remember from this image? There were flowers here, there was a mountain there, you don't remember the exact number of flowers, and you don't really care, right? Well, that's what our visual summary would generate, okay? This is what you get here. So what is it that we do here? I mean, of course, definitely we want this to be coherent given this. We want this to be likely given that, okay? But of course, if we crop only this region, it would still be likely given that. So that's not enough for a good visual summary. We also want this to be likely given that. We want this to be easily composed like a puzzle from this image. So we want this to be composed easily from this, and this to be easily composed from this. Or in other words, we want to maximize this bidirectional similarity or this bidirectional likelihood. And this is what we optimize when we generate these visual
sometimes we remember some details.
I'm sorry?
Sometimes we remember of an image the details that sometimes are of course are lost. Like for instance that there are in the sky some parts that are not. No,
obviously.
Depending on what you.
Wait, I have no notion of semantics. By the way, if there are things that are important to you, you could mark. You could say, this is really critical for me to be in the summary, and this is really critical, and we will just give them a higher importance when we generate the summary.
What's the difference in the script and message?
I can't tell you. That's not something that I.
But obviously, this is what you optimize.
No, what we optimize, okay, we want all the optimization itself is we want all the patches here at multiple scales to be here, and all the patches here at multiple scales to be here. Okay. If you take, I mean, the fact that all the patches here are found here means that we haven't lost any information. You can still build this back.
In my language,
Okay.
this is compression of the image. Actually, it's not the past, but it's an image which has some history in it, into something which you may call the relevant part or the useful part. And underneath, whether you explicitly do it or not, there's some sort of a compression scheme.
I agree.
Based on some assumptions of what's important, what's not important.
And also how frequent things are. For example, here there's a lot of redundancy. If things repeat a lot of time, you don't have to represent them many times. Okay, you can still recompose them from the. This is like each one of those flowers is likely given those flowers. Okay, so you don't need. This is your bottleneck. You don't need to keep lots of flowers in order to. Okay.
But there is an assumption that you don't explicitly tell us of what is important.
No, I don't. For me, everything is equally important.
So
right
the
now.
data itself tells you what's important.
Yeah, for me, right now, the way the algorithm works, everything is equally important. If you as a human know that you care more about something, for example, you care more about faces, you can say, this is more important for me, it will give it higher, the algorithm will give it higher importance than the
It's not everything equally important. The interesting are important because the sky, you lost some of it.
No problem.
If, for example, the picture was a small man, and on the background you see a huge blank screen, you'll throw away all the blank screen and focus on
the great thing about blank areas is they're so redundant, very small tiny blank area will generate all of them, so you have no problem. Okay, so that's you don't even have to say that. Okay, but there are things that are independently important to us. Well, for example, if your face is more important than exactly what you're wearing. Okay, excuse me. Okay, I'm not offending you. But that's something the computer cannot know. So if you want that to be taken into account, you have to mark that. Okay. If you don't mark that, everything would be equally important, of course, depending on how frequent it is. Okay. So here's another example. Here's an image. Here's the summary of that. Note that it was able to automatically detect the redundancy of these two buildings and map them into one. But on the other hand, it maintains the resolution of the car, the resolution of the house, and so on. Okay, so it exploits this redundancy of things, and it maps things as best as possible it can to this smaller constrained area. What happens in video? Same ideas, but everything in space-time. We want to take a larger space-time volume and map it into a smaller space-time volume. It can be smaller in x, smaller in y, or smaller or shorter in time. Okay, and again, we want this to be easily composable from this, and this to be easily composable from this. Okay. So here is, for example, an 8-second video clip of a ballet. Everything is important here. It's not you can throw away frames and so on. We want to shorten it to half the length. Okay. What do? Again, this is the summary that we generate in half the length. This is the input. This is the output. Okay. What happened here? It hasn't thrown away half the frames. That's not the issue. It didn't just take a bulk and threw it away. What it did is it tried to map all the space-time patches, multiple scales from here to here. Okay, that guarantees that it hasn't lost information, but it wants to generate something which is visually coherent. Okay, for example, if the ballet dancer did twice with her arm like this, once with a leg like this, and once with a leg like that, it doesn't have to maintain this thing twice. It's enough to keep this once. Or if it did twice with a leg like this, but once with her arm like this, once with her arm like this, it's enough to maintain this once, okay? And so it composes this new thing where each part here has been taken from this. It hasn't invented anything new. Every patch here space-time patch here exists there. So everything is visually coherent. We haven't introduced any new visual artifacts. But on the other hand, it tries to map all the space-time patches here to here to make sure that it hasn't lost any information. And this is what it's able to do. So again, let me show this one more time. Okay. So in a way, it's very different from the thing that Shmuel showed yesterday, because it wouldn't serve as a good index necessarily. Okay? It doesn't preserve the information. What Shmuel showed yesterday preserves the information. It hasn't lost any information. It just rearranges it in space-time. This is more related to things that we were talking about in terms of memory and things like that. It just gives you an impression of what happened in this video. Okay. All right. So why do we want to be able to talk about prediction of visual information? You see, prediction is important. Prediction of visual information, because we want to be able to detect what is unpredictable, unlikely, unexpected, and irregular. Those would be the most interesting things. They could be very dangerous things that we want to be aware of. They could be interesting things among clutter of uninteresting stuff. So this has lots of applications, ranging from detecting suspicious behaviors to being able to spot attention to something interesting very quickly, or doing visual inspection, detecting defects, malfunctions, and so on. Of course, you don't know ahead of time what these are. Okay, so for example, let's look at the problem of suspicious behaviors. We can't define ahead of time. Yes, sorry.
I want to ask about the video. What happens if you take, let's say, 10 minutes of a movie, any kind of movie, and try to squeeze it to 5 minutes? Will it count?
10 different movies?
No, 10 minutes of one movie.
And try to squeeze it?
I don't know, 5 minutes or 1 minute.
I think it's going to be terrible. No, at some point, if you try to squeeze everything. Oh, you know what? I'll show you a different example. I don't have it with a video, but I have it with an image. Okay? What happens if you take a big image and try to squeeze it into something that is too small?
Not too small, but let's say there is a movie, 3-hour movie that I don't want to talk about later, as if I see it, but I don't actually want to look at it.
So again, if you don't tell me anything about what's important in the movie and what's not, I'm going to do the best I can. The algorithm is going to do the best it can in order to preserve as much information as it can inside. Of course, at some point, the thing is too small to preserve all the information. So it will either throw away some of it, or it will superimpose things. It will do the best thing it can, but it will usually throw away things, not superimpose things, for the following reason. Remember, it has to be bidirectional. We also want to maintain coherence. Okay, so from the all equally incomplete things, it will try to select the one that is most coherent, because it wants the small thing also to be predictable from the large thing. And if you start averaging things, you'll start getting things that are not there in the original video. So it will start, and that's what the example I have with the image. At some point, it starts. It has no other option but to throw away things. But this may not necessarily throw away the things that you think are important, or are unimportant. But you could guide it. You could say, this is an important function, this is important, this is particularly important, go and summarize it. Okay? And then I think it will do a better job. But if you just don't tell it anything, use the Boyle's method. All right. Where was it? Suspicious behaviors. You can't define ahead. You can't teach a computer what a suspicious behavior is. You can't give enough examples. I mean, no matter how many definitions you're going to give of suspicious behaviors, there's always going to be things you haven't thought of. And it's actually worse, you can't even define all normal behaviors. The best thing you can usually do is give a few examples of normal behaviors and expect to ask, we were actually quite good at this, to generalize from that as to what is normal and what is not. And that's what I want to show here. Again, we're going to do this generalization or this prediction by composition. Okay? So we're given a sequence of what you see here is a person walking and jogging. Sorry. That's all I'm going on, by the way. Working with the answer. And we're going to say that this is an okay video. This is a valid video. Okay? No motion estimation, no segmentation, no tracking, no raw data. This is a good sequence of raw data. And now we're going to get a new sequence, and we're going to try to, with new behaviors, and we're going to try to infer what's likely and not likely in this new sequence. Okay. What we're going to do is we're going to try to check the likelihood of each and every point in this video according to how likely the region around it is given this reference sequence. How easy it is to compose the region around it from this reference sequence. How much savings in bits we get in each part here given this reference sequence. And areas that are likely, that are predictable, that get good savings in bits, they're fine. Okay. But areas that are easy to build, that need lots of tiny little pieces in order to compose them from the reference sequence, that don't get lots of savings in bits are unlikely. Okay. And those are going to be below a certain threshold. They're going to be highlighted in red in the bottom here. Okay. So that's a different person running, but it has no problem composing it like a puzzle from all and running. Okay. And so far everything's okay. But this is something it cannot compose easily from the video. Okay. And walking is okay. And also two people walking. It's never seen this, but it's able to compose this like a puzzle from the reference sequence. But this strange walk, this is something it doesn't know how to predict from the video. And we didn't have to teach it that this is suspicious behavior. It says, I don't know what that is. Given what you've shown me so far, I have no idea what this is. It's completely unpredictable. or take a look at the guy in the front, he's going to stand up in a few seconds, and at that point he will no longer be highlighted in red because this is already easy to compose from the reference sequence. And we didn't have to tell it that falling is an abnormal behavior, or that jumping above the chairs is.
Do you think that
And running is okay, but not running with a chair.
Do you think that it's possible to add an active learning phase in order to understand what is become more frequent, so become normal and so not suspicious anymore?
You mean over time?
Yeah.
Yeah. This thing you can here we had a reference sequence of it, but you don't necessarily have to have a reference. You could, if I answered your question correctly, you could have a video and say, what is abnormal given what I've seen in the last 1 minute or half an hour and so on.
Okay. But
but you get this is in a way the adaptation that we saw yesterday. Okay, you get adapted to it. You say, that's okay. I've already seen this. I don't get excited by it anymore. I think that's got a lot to do with what we saw yesterday. But then all of a sudden something happens that you don't know how to explain given what you've seen previously. So that
you can decide just study about the frequency of the behavior. Of course, it's sometimes
frequency and size and how difficult it is to compose it at random. It's not just frequency. Okay, yeah. Sorry?
If you use different patterns, you would have to change the threshold of what's in the thing for every pattern.
Here we didn't work much with a threshold. We just took manually. We selected the threshold and so on. I don't think, other than just guessing, I don't think I can give a very scholarly answer to your question, because I haven't. If you say it's different, it shouldn't. But I don't want to say for sure because we haven't done this extensively. So I'm not sure. Yeah.
How heavy the computation can it be done in real time or?
Okay. First of all, by definition, nothing we see here is in real time because this is all research code. Okay, MATLAB research, but most of these things can be done in principle. This is superlinear. In practice, we have recently been able to do these things using randomized search and actually sublinear computation. But by the way, this thing is doing it with a randomized search, growing these regions in a randomized search is something very new that I hope you'll be writing a paper on that soon. But that should address this issue. But nothing I do is in real time. But that's just a malfunction of nothing. When we do research,
You have some idea about training.
yeah, no, I can say that lots of the things we do is linear type of the data. Okay. This used to be superlinear because we used to look for each pixel. We used to look for its nearest neighbors to seed the growing region growing, and in principle nearest neighbors ON log n, if you're approximate nearest neighbor. Of course, once you grow a region, you can assign it to all the others, so you don't really have, so it gets close to linear, but still, it can be, you can't guarantee. But things we're doing now is using, again, the wisdom of the data, or what you call it, let the data guide you, or whatever. If you take things and you randomly look together for regions, and then one of the guys finds a region. It's very similar to patch match, for those of you who know it. But patch match, again, looks for an approximate nearest neighbor, and so spends most of its time on finding pixels that are very that are isolated, and therefore it still doesn't go beneath ON log n. But here we're looking for large regions. Large regions, it's very, once at least one of the pixels found something similar, it can propagate it to all the others. So each guy looks elsewhere in the image in a random way. And whenever somebody finds something, he calls the other guys, and they all go there. And that can be done. If your region is not small, not too small, and we're not looking for too small regions here, it can be done very efficiently. Okay, and you can show that with high probability very quickly you'll lock onto this region. Okay. Often we don't need any example whatsoever. Here you had a reference sequence, and you could, and we gave something new. But often you have no, and you don't need any reference. If you're in a stadium and there's a cheering crowd, and all of a sudden somebody's running in this crowd, you immediately spot him as being fake. Okay. Or if I show you this sequence, and you'll immediately tell me that the person in the middle is behaving in an abnormal way, even though I didn't have to tell you that raising and lowering your arms is a normal behavior. The notion of normality is in the datum itself. And indeed, if we apply the algorithm to this, and this is what I said, the prediction doesn't necessarily have to be sequential. What you see here is all the regions that are not predictable from other parts of the same video happening more or less at the same time. Okay, so whatever is easy to compose from other parts, whatever you get lots of savings in bits from other parts of the video, okay, those get high likelihood. And whatever is difficult to compose from other parts of the same video is not predictable from other parts of the same video happening at the same time. That stands out as being salient. Okay, and that's what's marked here at the bottom. And of course, this is also good for detecting defects. Again, I don't think I need to tell you where the defects are here. You have no problem spotting them. You've never seen those images before. Why does it you easily spot them? Because they're not predictable from other parts within the same image. Again, it's not sequential prediction. That's what I meant to predict. It doesn't have to be
when
sequential.
I look at images, I generate a sequence.
No, but that's the funny. Okay, the funny thing is, I don't think you look at. That's what I said. It's not a thought of straw. You jump to. By the way, you really randomly jump to places. Okay, you start to. Anyway, all right. So if we apply the algorithm here, indeed, it finds all the red regions as regions that are not predictable, or not easily composed from other parts of the same image, and those are the defects.
As easily.
I'm sorry?
Not as easily.
Not as easily composed, yeah. And so far I showed how exploiting this internal redundancy of data, how the fact that things repeated within a lesson can be used for detecting similar objects in action, for predicting visual information, for talking about likelihood of never before seen visual information, for generating visual summaries, for detecting the irregular and unexpected. But it can also be used for exceeding optical bounds of visual sensors. For example, super resolution. In super resolution, what we want to do is we want to take an image and we want to enlarge it. But if you just enlarge an image using a computer, you interpolate it, or you just stretch it, you don't really get new information which is smaller than a pixel size. You can't go beyond the Nyquist limits of this thing. You're limited by the sampling of the camera. Now in super resolution, we want to be able to see fine details that are smaller than a pixel size. Okay, and for that, typically people have used the classical schemas. Let's take lots of images of the same scene at subpixel shift, combine the information from all of them at subpixel accuracy. This gives me a higher sampling rate of the scene, and therefore I can recover a super resolution of the scene. But the question is, can we do this only from a single image when we don't have lots of images? Can we still exceed the Nyquist limits of the sensor? And the answer is yes. Again, this is recent work with Daniel Glasman and Shai Bagon. And the reason we're able to do this is, again, because of the observation that small patches in the image recur many times, both within the same scale and across different scales. What do I mean by that? What do I mean within the same scale? If I look at this patch, here are other occurrences, very similar occurrences of this patch. Or this one, here are other occurrences of these. Okay, now if I treat these as different images of the same part, and these will inevitably be at subpixel shift relative to each other, then I can start obtaining super resolution of those regions, or in other words, I can translate these into the classical super resolution equations, only this time from a single image. Okay? But these are not the only kinds of representations I have within an image. Patches also recur across scale. What do I mean? If I take this image and scale it down, okay, and then if I look at the patch here, then this patch is found as is, very similar to it, but without scaling the patch down, in a smaller version of the image. Okay. Now this one, I know how this guy looks like when he's in high resolution. So this gives me a hypothesis of what this might look like in high resolution. So this is what we call example-based super resolution constraints. And people have typically done example-based super resolution, but using an external database of images with examples of high resolution, low resolution, external examples of high resolution, low resolution. Here we do it for multiple resolution within the same image. So all of these patch repetitions can be translated into linear sets of equations, either if they're within the same scale as subpixel shift, the classical super resolution equations, or if they're across different scales, the example-based super resolution equations, and this forms the basis of the algorithm, and I will not describe the algorithm in more detail, but I do want to say something. This looks like a very contrived example. You can say this is a very repetitive image, but it turns out that if you go to small enough patches, say 5 by 5, then this patch recurrence occurs in almost any natural image, regardless whether it's an indoor or outdoor image, a man-made or how natural. And we tried to quantify this, and we asked ourselves, how many 5 by 5 patches within a natural image recur 10 or more times, for example. Okay? So if you take a patch, you can ask, how many times can I find it in the image? And you can start plotting a graph, and it turns out that about 90% of the patches within an image, 5 by 5 patches, recur 10 or more times within the image. Now you can repeat the same thing, but this time on a smaller scale of the image. Again, taking the patch as is. Okay, we're looking for it inside an image which is 75%, and it turns out that still close to 90% of the patches in this image recur as is in the smaller version of the image. And you can do it again for a smaller version of the image with half the scale or a quarter of the scale. And again, it turns out that around 70% of the patches in this original image recur as is 10 or more times in this tiny little image. Now this is of course not only for a single image. This is we measured the statistics over hundreds of natural images over the Berkeley segmentation database, and this is the mean, and those are the variances. Okay, so this is a very, very strong phenomenon of natural images. Sorry.
How do you measure the number of times they occur? Is it like a threshold of L2 distance?
Okay, so what we did here was the following. It's a very good question. L2 distance, SSD would not be good enough in this case, because uniform patches would have low SSD, whereas a patch with a strong edge would, even if you find a very good localized patch with the same, it would have high SSD. That's some square difference, okay? It would have a high L2 norm. So what we did is, for each patch, we shifted it by half a pixel and measured the difference between itself and its shifted version by half a pixel. We shifted it by half a pixel in a different direction. And took the maximum of these, and we said, if something is close enough to this within half a pixel, if, according to itself shifted by half a pixel, then we say it's similar. And this is the threshold. Okay, I mean, it's this times 1.5 we took or something. I can't remember that. The threshold was taken to be, but it was patch dependent.
Given those shifted patches,
and the L2 distance, but the threshold of that was determined by how I just said. Okay, so you can't take a uniform threshold for all of the patches. So this forms the basis for the algorithm. Okay, every patch repetition, we look for nearest neighbors for each patch in a different scale. Every patch repetition induces an equation. We weight this equation according to the degree of similarity of the patches and resolve the set of linear equations. So let's look at results. So here is an image. Here is bicubic interpolation of this image by a factor of 3, and bicubic interpolation is a relatively good interpolant. Here is the result of our super resolution algorithm. Let's zoom in on a small area. This is not super resolution. This is just, I'm enlarging it because it's difficult to see here the differences. Superimposing, and let's flicker between them. So bicubic interpolation, super resolution. Bicubic interpolation, super resolution. Okay, and you can see that the edges get much sharper. But remember, in super resolution, we don't want to just get sharper looking edges. We want to find new details that are smaller than a pixel size. Okay. And by the way, there's a recent work by Raman Fatal and people here at the Hebrew University, which does something very similar to this, only they do it much more efficiently than we do. They look locally in scale, and they look for similar patches locally in scale beneath the same location of where you are. This speeds up the process extremely, but it does not allow you, it only gives you sharpening of edges. It will not allow you to recover new details that are smaller than a pixel size. In order to find these details, you have to go elsewhere in the image in a different scale, and that's what I'll show you now. So really, to obtain super resolution, you cannot stay local. Okay. So here's bicubic interpolation, and let's look at this area over here. You see this P over here? There should be a hole there. Okay. Here is the result of our algorithm. Now this hole, you don't see it in bicubic interpolation because it's smaller than a pixel size in the original image. It's just below the Nyquist limits. But here's the result of our algorithm. Now, it's not that there's any P up there. It didn't copy anything. But the upper part of the P is similar to the upper part of an R, and the lower part of the P is similar to the lower part of an H, and it's able to compose this new configuration and it thinks it's a likely one, even though it's never seen it, because it found enough evidence so that these things go well together, okay, from little patches in other parts of the image at other scales. And again, note that if you were to just look at the coarser resolution in the same location here, you'll never be able to recover this hole. Okay. So here's a more natural-looking image. Here is the eye. Bicubic interpolation, our result. Let's look at an area over here. Bicubic interpolation, our result. or look at this image. Look at how much bleeding you have here in between. This is bicubic interpolation. It's again, it's below the, it's just beyond the resolution of the sensor. Here is the result of our algorithm. And again, bicubic interpolation, our result. Again, in order to know that this thing should be split, it doesn't have to go coarser in resolution here. You have to see it elsewhere in the image, in a different scale.
To make sure I understand that there's obviously you create artifacts.
Oh yeah, I can show you artifacts.
And the information is not for free. I mean, you get it first because there are actually many repetitions.
Yes, and in places where there are no repetitions, you generate nonsense.
Yeah.
I can show you. You want to see some nonsense?
Yeah, of course I want.
Okay, I'll show you the nonsense. By the way, they don't occur a lot, but they do occur. See this thing? This used to be a question mark. It does this point. This is the only place. I mean, you don't. It's not that you see it very well in the bicubic interpolation either. Okay, but this is where is it? I can't even see which one it is. It's this one. This is the question mark in the bicubic interpolation. Okay, but it doesn't have this. Maybe if it had an eye with a point, it would have been able to generate this. But there was nothing similar to this particular thing, not as a whole, but even to its tiny parts. So it generated nonsense.
But you're not violating Nyquist. I mean, you do because in some sense Nyquist is a pessimistic bound because it assumes that it doesn't use the global redundancy and you use it much better.
Yeah.
This is actually very similar to the work of Yonina Eldar and others at the Technion now on going below Nyquist and signal processing by essentially using dynamic spectrum. And essentially she can show that if there are holes in the spectrum, even if they are not known a priori, you can beat Nyquist.
And the redundancies are in the spectrum or in the spatial domain?
So no, it's
in the frequency domain.
Processing domain essentially. That really, of course, comes from the, but it's the same, exactly the same principle. You use the redundancy of the signal, which in that case means that there are some holes in the spectrum, to learn global things which are not taken into account in the simple Nyquist Fourier representation.
Yeah.
And in that sense, it can be applied, and I know you're trying to apply it to speech and to other things.
So let me skip all those things that you've already seen. And just one more example. I like this example because if I show you this balcony, it's obvious to you there should be a handrail here. And you know this because you've seen it elsewhere in the image. Okay, at a different scale. So it's clear to you there should be a handrail here, but you don't see it. And if I zoom onto this, if we look at the bicubic interpolation, of course it has no evidence of the rail. And this is the result of our algorithm. It's not perfect, but it did something. Again, look at bicubic interpolation is both doesn't have the rail and is more noisy. Okay, this is the result of our algorithm. Because it's less noisy, sharper, and also was able to recover the handrail. And the reason it was able to recover the handrail is because it has evidence to it elsewhere in the image in different scales. And by the way, note that no external database will give you this evidence. The only evidence to the existence of this rail is internally inside this image, which leads me to the final thing I want to show, which is just 2 slides on a recent work that we've done. We've tried to analyze more extensively this thing of statistics of a single natural image and where things recur in the image, and I won't go into all of this now, but I do want to talk about this internal versus external statistics, because often people look at this problem of solving ill-posed problems. We have an ill-posed problem, for example, the super-resolution problem. We need to give it some prior because it's too ill-posed. We want to take a low-resolution image, generate a high-resolution image. If it's a single image, it's obviously ill-posed. So people give it priors like regularizations that we've heard earlier this morning, or other types of priors. And people have also used external statistics from statistics collected from lots of natural images. But what I showed you now is how you can do it from internal statistics. And of course, people have used internal statistics for other types of solving ill-posed problems, such as denoising. For example, non-local means uses actually the patch repetition inside the image in a way as a prior for solving this ill-posed problem. Now the issue is that internal statistics is we use patches from a single image. And of course, in a single image we have a limited number of examples. Whereas in external statistics, we have an infinite number of images outside the internet or whatever. Obviously, we have unlimited number of examples externally. So it seems like external statistics should be better than internal statistics. What we've shown in this paper is that internal statistics is often not less good and often even better than external statistics in various ways. And I won't go into the details, but I want to say a few observations we have. One of we measured, I'm out of time totally. Okay, sorry, this is the last. No, not at the expense of you. I have to keep me on good terms. So the patch, we measured the empirical patch entropy. So internally, the patch entropy is much smaller than externally in a random collection of natural images. And also the other observation we had is the predictive power of internal statistics. Even though it has a limited number of examples, its predictive power is much stronger. For example, what I showed you before about the balcony is a visual example of what we mean by this predictive power. Internally, you often have much more evidence to what really you need than externally in a random collection of images. Okay, and just to show it again, example by super resolution. Internally, you have low resolution, high resolution patches taken from multiple scales of the same image. Externally, these would be taken from different scales of external sets of images. And the problem with super resolution is, as we say, example-based super resolution is you may hallucinate nonsense, like the question mark I showed you now, because a single low resolution patch may have, in theory, multiple valid high resolution parents. I mean, these could have additional high frequency information that is not contained here. And different examples may provide different suggestions of what the high resolution parent should be, and you don't know which one is the correct one. So you may hallucinate nonsense. Okay. What we've been able to show in this paper is that external databases tend to produce more hallucination than internal one, and we've empirically verified this over hundreds of natural images. And moreover, that the larger the database, actually the larger this uncertainty is. Okay. And I'll finish with this visual example comparing these two. So here's the natural-looking image. This is super resolution using only internal examples. This is super resolution using external examples from an external database of 200 images. Again, internal, external, internal, external. And you can see that there's much more uncertainty and hallucination when we use external examples. So, let me summarize before time kills me. So I hope I've been able to convince you that there is lots of redundancy and it's very useful inside natural images and videos, and that by integrating these local similarities within the datum or across different data, we're able to perform very complex visual inference tasks, often without any prior examples and without any prior training. And this gives rise to various applications, some of which I have time to talk about: detecting similar objects and actions, predicting visual information, detecting irregular, unexpected super resolution from a single image, visual summaries. I didn't have time to talk about image segmentation, and I mentioned a bit about the comparison between internal and external statistics. And what I'm trying to say, the information is already there. There is so much spatial redundancy in images. There is so much temporal redundancy in video that if we're able to detect it and exploit it, this gives us all the statistical information we need in order to perform very complex visual inference tasks. And I want to acknowledge all the people who worked with me on these things. Eli Shechtman, Yoni Wexler, right here. Oren Boyman, Daniel Gladner, Shai Dagon, Denis Simakov, Yaron Kaspi, and thank you for your attention.
All right, so we have time for maybe one or two short questions. Keep the rest of the discussion.
Referring to gathering external statistics, if you concentrate on...
Speak up, I can't hear you.
When gathering external statistics, if you know the type of image you're expecting, say only text, do you expect that super resolution using external statistics might...
Thanks. I forgot to say this. Thank you for your question. When I compared internal versus external, I compared it to a random collection of images, not images from the same class. Okay? If you want to do super resolution of a face image and you have an external collection of face images, then I think you'll have many more examples, and they will be useful examples. It's when you use a random collection of images, just without not class statistics, and you come for each image, find the class specific correct set of images. You know, this part will be one class, this will be another. If you just use a random collection of images, I think it's better to stay internally. Okay. And by the way, I didn't talk here about denoising, and denoising is a different issue, and I won't talk about that, that you will kill me. But there, even class-specific images may not be good enough.
A very stupid question, I'm sorry. Of course, if you have information... Oh, I'm sorry. I'm sorry because I didn't know.
No, it's all right. I just get all sorts of signs there that the food is outside.
Okay.
Maybe we'll switch.
I can ask you to do it.
Okay.
Did I talk for that long?
No, but we were late anyway, and then she learned from yesterday that she didn't look at the new schedule after the shift of 20 minutes. Anyway, since I don't want you to have cold food.
Okay, keep asking Michal, and then we'll take a break and have some lunch. Another question?
Okay, but it's just about the possibility to include some semantic search also, and not only. There are some specific applications where you know what you need to, what you have to apply super resolution. So in this case, maybe as itself for the face, if you have a database of face, you can do. I was thinking about the typical application security of super resolution of number plate recognition of a part and details of something. In some cases, you can have similar in video, because in video you can use the video in order to have this, or you can have other database of numbers or so on. So do you know if you have information about what you are looking for, the
undoubtedly.
increment or not necessarily?
No, undoubtedly. If you know if you have a restricted domain, by all means, use additional information. And if you have a video sequence, don't throw away the things. Use all of them. No, that's undoubtedly. I'm not saying here don't use any additional information. I'm just saying use it wisely. And when it's available. When it's too difficult to get it, like all I'm saying is when you want to find similar images, similar things, you can't always define ahead of time all these classes that you're looking for. You can still do a lot of things even without this kind of information. But if you have additional information, by all means use it. I'm not against using extra useful information. I think you should.
Because sometimes it could be overfitting.
No. But so overfitting is a problem. And by the way, denoising, that's the strange thing we found, that if you use external denoising, okay, in a way you think internally your patches are noisy. Externally your patches are clean. Seems like for denoising, externally should be much better. Turns out you do hysterical noise mixing. And you have such a large database, you have lots to this to overfit to. And actually it's not. Even if it's the same class, by the way.
All right, so we'll make a spontaneous change of schedule and have lunch now. And come back, let's say, try to do it 1:45. Or 20 past.
No, I'm going to come out in general.